All right, guys, now I'm going to talk about a different type of problem that we're going to deal with. Um, we're going to look at this idea of a Ferris wheel again, and I'm going to pop up a little circle here to kind of show you. So we have a circle over here, and we have a dot on the outside. Now, what actually happens is, as you're moving around on the Ferris wheel, you see that that dot is moving around. We have to have a way that we can actually calculate how high, or what is the height of that dot at any given time based on this circle. So what I'm going to do is I'm going to go through a process of, I'm going to use that Ferris wheel from 1893 again as an example to actually show how we can calculate the height of that dot or that person at any given time. Now we use that to find the angular and linear velocity, and that's great, but sometimes we actually need to know the position in space as well where they're actually at. So let's look to see how to do that actually. Okay, so I have my Ferris wheel right here. Now we know from a previous video that this is Ferris wheel. It took 10 minutes to revolve around. So I'm just going to break this into different angles so we can actually look to see. But we do know that the diameter was 264 feet. So we know at this point right here, that person is 264 feet above the ground. And we know right here, if this forms a 90-degree angle, well, that's just going to be a radius, and this person would be 132 feet above the ground. But what about if you were right here? Let's say call this 30 degrees. How would we figure out how high they are? Well, we're going to draw in a little triangle here. And really what we need to know is this distance right here. We need to know that distance. Believe it or not, there is actually a trig function for that. That part is actually called versine of theta. So that's actually fairly straightforward to calculate. Now this is based on a radius of 1, but we're not really going to talk about that. It's not even programmed in onto your calculators, but there's an easier way to actually think about it. This is a neat little historical trick, which actually makes this problem quite simple, and I will show you kind of why I say that. So the first things first is I need to know this whole length right here. I know that the whole length is 132 feet because it is a radius. I then need to know how long this part of the triangle is. Because if I know how long that part of the triangle is, I can just take this minus this and I would get this little part. Well, I know that this part here is another radius, so this is 132. So I can actually have a triangle, 30 degrees, this is 132 feet, and I need to know this distance right here. So what we're going to do is we're going to do cosine of 30 degrees equals x over 132. Multiply both sides by 132. That's an S. Cosine of 30 degrees, that's going to be my x. So when I do that, I simply get, let me pull up my calculator here. Where is my mouse? Make sure that I'm in degree mode, so I'm going to hit mode here. Look to see, oh, I'm in radians, so I want to scroll down. Go over to degree mode, hit enter. Now I'm in degree mode. I hit second quit, and I'm going to do 132 times cosine of 30 degrees. And that gives me x is about 114.3 feet. Now that's not my answer. I'm looking for this little part right here. So what I need to do is 132 minus 114.3 feet, which then I'm just do 132 minus my answer, and I get 17.6, well let's call that 17.7 by rounding. So 17.7 feet. So when you're at this point, you're 17.7 feet above the ground. Now, what's really nice is really all I have to do, if I think of terms of versine, and versine is actually has a trig identity, what we call, and this becomes 1 minus cosine theta. So I can actually write 132, because it's based on versine, is based on 1. So 132 times 1, versine of 30 degrees. And now with this, versine is not built in the calculator, so I have to do 132 times 1 minus cosine 30 degrees, and it should spit out the same answer. So let's look. So we're going to do 132 times 1 minus cosine 30 degrees, close, 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 and we get the exact same answer. So if you want to think of it in terms of versine, I'm not going to hold it against you, but just know that this is not programmed into your calculator. And you would have to do 1 minus cosine theta and just multiply it by the radius. What's really nice is as the angles change around this, it will actually immediately give you your answer. So if I wanted something, say, way up here, right? I want to have my triangle here, but I have this huge angle right here, and let's call that 135 degrees. So all I would have to do would be 132 times 1 minus cosine of 135 degrees, and I would have the height of this point right here. It's all taken care of for you within this. So versine actually trivializes this type of problem instead of having to break it down into individual components how it's normally done. So not terribly bad. What I'm going to have you do is work a bunch of these, because we're going to take this and we're going to use it tomorrow. So whenever you're doing your work today, write that down on a piece of paper and everything with the angles and the heights and everything else, because we're going to use this. We will use this tomorrow in our actual lesson to basically make a graph. Hi, I'm Mr. Buzzard, and these videos are supplemental instruction for my students. If you found the video enjoyable, make sure you click the like button and click subscribe, as well as the bell for notifications to receive future videos on high school mathematics.